All right, let's get started. Let me just. Our notes from last day. Where did we put them? Blah, 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 blah. Okay, so I know, sun's out, everyone's excited. Okay, so we're gonna start kind of reviewing. It was just on Monday, so not that long ago, right? But we're just gonna finish example 4 and then head right into example 5 because we covered all the binomial theory last day. So now we're just looking at examples. How do we actually do these problems, right? And then we're gonna head into the Poisson, and I'm really hoping that we can get into chapter 7. Might be wishful thinking, I don't know. Oh, last night I spent about 40 minutes making videos, but forgot to share my screen. Facepalm emoji. I could not believe it. So anyways, I posted the solutions. I'll see if I get around to redoing them in a video. If you have any questions about those, there's audio, but it's just a blank screen. The worst. I could not believe it. So anyways, could not believe it. So from last day, but like I said, I did post the solutions to example 2 and 3 on Moodle, right? Just the PDF, so you've got that at least. And then let me know if you have any questions. From last day, right? We need to finish example 4. So we did A through E, right? I kept you guys until down to the wire. We finished that probability, right? And just to have a brief look at it, oh, it's today, here, right? That last probability of, what's the probability of the index increasing in more than 3, not including 3 of the weeks, right? So that's an increase in 4 of the weeks or 5 of the weeks. So what we said was, okay, I have to find the probability of 4 successes and add it to the probability of 5 successes, right? And so I break it up and do them individually and then put them back together. And we found that the probability was 0.2714320896. You have to keep as many decimal places as you can on your calculator, right? If you know how to store values on your calculator, which I still don't know on this one, it's okay. I don't mind plugging them in, right? But you want to keep as many decimal places as you can. Because sometimes the probabilities don't start changing until kind of down here in these decimal places. So then if you're rounding, you're not really getting a good view of the probability. So the last question that we didn't have time to do last day was just to find the mean and the standard deviation of this distribution. Now we already said that this is a binomial distribution, and we said that n is 5, right? We're looking at 5 weeks, so we have 5 opportunities for a success, which is an increase. And the probability of a success was 0.56, right? The probability of a stock increasing in any week. So part F, we said that we can find the mean mu by just calculating n times p, right? This is probably what you would do in your head, right? If I asked you, so I said, okay, you're going to try something 5 times. The probability of a success is 0.56. How many successes would you expect to see, right? 5 times 0.56, right? Or if you want to think about it in kind of numbers that we can actually do, right? I tell you that you're going to try something 10 times. The probability that you succeed each time is 0.2. How many successes do you expect to have, right? 10 times 0.2, so 2, right? And so that's what we're doing. So mu here is going to be 5 times 0.56. So 5 times 0.56, I get 2.8. So we have a mean of 2.8 successes, right? 2.8 weeks out of the 5 is how many times we're expecting to see an increase, right? We can't have increases in 2.8 weeks, but the expected value doesn't have to be an actual outcome that we can observe, right? It's what we're expecting to see. And the standard deviation sigma, from your formula sheet or just from your mind, n times p times 1 minus p. 1 minus p, right, is the probability of a failure. P is the probability of success. 1 minus p is the probability of failure. And we said sometimes we write 1 minus p as just q if you want to cut down on writing a tiny bit. Nothing major. So we want the square root of 5 times 0.56 times 1 minus 0.56. So we do 5 times 0.56 times 1 minus 0.56 in brackets, right? Just be careful. So I get the square root of 1.232. Oops. Don't forget to take that square root. I get approximately 1.109954954. So that's my standard deviation of the number of increases that I'm going to see in each week. Nice. Good. Are we ready for example 5? Okay. Example 5. You know what? I'm going to put it on its own page. So this we'll call kind of the end of the review. It wasn't really review, but it was finishing up from last day. So call it what you want to call it. New question. Suppose that Canadian Blood Services anticipates the need for at least 1,850 units of O-negative blood for a particular region this year. It estimates that it will collect blood from 32,000 donors, and only about 6% of people have O-negative blood. Okay, so that's a problem. So we're going to work through and figure out what's the success, right? First thing I would probably want to argue is whether this is a binomial question or not, right? And so definitely when we sit down for test 2 and on the final, right, the first thing you're going to want to do is to try to figure out what type of question this is, right? And so we want to start kind of reading these and trying to figure out, okay, where can I classify this problem, right? It sounds like it might be a probability problem in the sense that I'm not given a mean or a standard deviation, right? I'm not told that it follows a normal distribution or anything like that, right? So z-scores are kind of out of the equation for now, right? And so I can divide the population into either you have O negative blood or you don't, right? And so now I've got this kind of binomial distribution, right, where I can have just two possible outcomes. Of course, we know that there's other blood groups, right? But if we're only concerned about O negative blood, right, we can consider that a success and then everything else a failure, right? And so we can boil it down to a binomial distribution. So we'll start by just kind of justifying the binomial distribution. So the binomial distribution is appropriate here because, and I'll list them, number one, the first thing that we're going to look for is, do we have a success-failure situation, right? We only have two outcomes, right? O negative blood versus not, right? So we can call this a success-failure situation. So that's good. So that's one of the things that we need to have a binomial distribution. The second thing is that each of these outcomes have to be independent of each other, right? My blood type, I can reasonably say, is independent of all your blood types, right? And so on and so forth, unless we're talking about maybe siblings or whatever, right? But if we've taken a random sample, there's no reason to think that we're going to have dependence between our blood types, right? So we can assume that all these blood types are going to be independent of each other. So we can reasonably assume blood types are independent from person to person. So those are the two main things that we want to look out for. If we think we might have a binomial distribution, we're just going to check these two things.
Would we have to justify it like that on a test?
No, it's just for you kind of to convince yourself that you're going to work through and do the right thing. But no, that would take too long. Yeah. So, okay, so we've decided that we've got a binomial distribution, right? We can model these probabilities with a binomial. So now, right, if it wasn't part of the parts here, we would try to identify, okay, what are we going to consider a success? And then how many trials do we have and what's the probability of a success? All these things would be given in the problem, right? They're not necessarily going to be parts in the question, right? You would have to kind of come up with these things on your own. But here we're guided. And so a success is going to be someone who has O negative blood. O negative blood. B, what are N and P in this case? So in this case, N is going to be the number of trials. It's the number of opportunities that we have to find someone with O negative blood. It's the number of opportunities that we have for success. So the number of people that we're looking at is going to be 32,000, right? It's all the donors, because they'll either have O negative blood or they won't, right? And so don't get kind of caught up in the 1,850 units. That's how many units of O negative blood that we'll need, right? That's how many successes that we'll need at least out of these 32,000, right? So that's for later, probably, right? Where we try to answer this problem. But as far as our N goes, that's going to be our 32,000. And then the probability of a success each time is going to be 6% or 0.06, right? We convert it to decimals always. So N is going to be 32,000, right? And I'll kind of justify it here. Each donor is a trial, right? N is the number of trials, and so each donor is a trial. We can consider that a trial. P is 6%, right, or 0.06. The probability of success is 0.06. Okay, part C. What is the mean and the standard deviation of this distribution? Right, what's nice is we only need to know N and P, and then we'll be able to calculate these, right? And so we just established what N and P are, and so C, the mean mu is going to be N times P, which is going to be 32,000 times 0.06. So mu is 32,000, make sure you get all those zeros, times 0.06, 1,920. So far, things are looking good, right? This is how many O negative donors I would expect to have in a sample of 32,000, right? So far, things are looking promising for that 1,850 that we need, right? So let's figure out what our standard deviation is so that we get an idea of the spread. So that's going to be the square root of NP times 1 minus P. So that's going to be the square root of 32,000 times 0.06 times 0.94. Did it in one kablam. Oh. So now 32,000 times 0.06 times 0.94. I'm going to take the square root of 1,804.8. Puts me at roughly a standard deviation of 42.48293775. Now, we have some idea of the spread, right? A spread of 42.5, let's call it, right, is pretty wide. So we'll see how that affects our probabilities. All right. So we found the mean and the standard deviation. And here, part D just says, set up the formula for getting exactly 1,850 units of O negative blood from 32,000 donors. So we're just going to set up the formula. We're not going to do this calculation because I'm pretty sure your calculator won't be able to do 32 choose 1,850. It cannot. Way too many. Because what are we saying? Imagine a tree diagram with 32,000 layers, each with only 2 possible outcomes. Ugh. And then we want to figure out how many of these branches, even if we did map them out, how many of these branches have exactly 1,850 successes. Yuck. Even your calculator is like, no thanks. So we're just going to set up the formula, right? And then just be really grateful that we have the normal approximation to the binomial, where we can just kind of say, if I have a large enough sample size, then I can start thinking about this as a normal distribution, which is way easier for us to deal with, right? And so here we go. We're going to set up this formula, because we still can, right? We want 1,850 successes in 32,000 trials. Remember, we denote K as the number of successes. So in general, let's write down our general formula first. The probability that X equals K, and I do a script K, otherwise, I don't know, looks weird, is going to be N choose K, which we talked about last day, right? The choose function on your calculator. And so N choose K times P to the power of K, right? The probability of success to the power of however many successes we need, times 1 minus P, that's the probability of failure, times however many failures we need. If we have K successes in N trials, the rest must be failures. Okay, so now we want the probability that X, which is the number of successes, is exactly 1,850. So wherever we see a K now, we're going to replace it with 1,850. Okay. N is 32,000. K is 1,850. P is 0.06 to the power of 1,850 times 1 minus 0.06, or 0.94 if you want, to the power of 32,000 minus 1,850. Kind of ran out of room there. We can simplify this a little bit, right? Not too much. 32,000 choose 1850 is 0.06 to the power of 1850 times 0.94 to the power of 32,000 minus 1850. 30,150. That's what we would do. Computers can do it, right? You'll see it in lab 6 where you actually use Excel to calculate. You can calculate big probabilities like this. It's actually going to be a very small probability, right? So as to make room for all the other outcomes too, right? And so the probabilities can be very, very small, but big in terms of the numbers, right? And so Excel can do this. We cannot on our little calculators, right? And so I'll make a note here. Our calculators can't handle this calculation. I haven't tried it in Excel. It might even be too large for Excel to handle. We'll try it on Friday. Excel, I'll even go out on the limb and say we'll likely be able to handle it. Right. So lab 6 just goes through and shows you how to do all these z-score calculations, binomial calculations, Poisson calculations using Excel, right, instead of by hand. Okay, so there we have it. That would get us the probability of exactly 1,850 O-negative donors. Now, if we just kind of skip ahead to part F for a little bit, how likely is the Canadian Blood Service to meet its need of at least 1,850 units of O-negative blood? So at minimum, we have to have 1,850, right? That's the calculation that we just set up, we did, let's call it. But then we would want 1,851, 1,852, 1,853, all the way up to 32,000. Add those all up. Sounds terrible. Slash probably a good month's worth of work. Like, not worth it. So that's when we have to check the assumptions for the normal approximation. If we can use the normal approximation, then we can go ahead and just estimate these probabilities using z-scores. Okay, so first we have to check the assumptions. And so put it on a new page. We're going to check the assumptions for a normal approximation. What were the assumptions? The assumptions are that we have, or that we expect to see at least 10 successes and 10 failures, right? So our sample size has to be large enough to handle 10 successes and 10 failures. In fact, the sample size has to be large enough, but also the probability of a success that we're trying to detect has to be large enough. If the probability of a success that we're trying to detect is 0.0001, we would need a really, really large sample to try to get at least 10 successes, right? So it depends on our probability of success, our sample size that we would need, right? And so the assumption is we need to expect at least 10 successes and 10 failures in our sample. So how do we calculate that? Well, we said that if we do n times p, that's the expected number of successes. Right. So here, this is the expected, kind of all of this, I guess. Lost my n. Expected number of successes, right? So we can calculate n times p and just make sure that it's larger than 10. Right? We can even say larger than or equal to, it's pretty flexible. If it's equal to 10, maybe use some caution, right? But generally things are gonna be, these numbers are gonna be really big, right? And so it's not gonna be a concern. And we also need to check that n times 1 minus p has to also be greater than 10. N times the probability of a failure, right, is the expected number of failures. The expected number of failures. Okay. So in our case, right, we can check n times p is going to be 32,000 times 0.06, and I'll go across the page, even though it hurts me. 32,000 times 0.06 1,920, which we actually already found, right? Which is greater than 10. And so I'll put a green check mark there, right? 1,920 is larger than 10, great. So let's just check the failures. These conditions will always pass, right? If they don't, we won't be able to do the rest of the problem. I wouldn't set up a problem like that, right? It's more for real life. If you're checking, can I do this, right? Can I use the normal approximation? Then you're on your own and it might fail, right? But generally, if you think you have a large enough sample, you probably do. Right? So if we do n times 1 minus p, which is 32,000 times 0.94, 32,000 times 0.94 is 30,080. Notice that the number of successes plus the number of failures has to equal n, right? That just makes sense. So however you arrive at the 30,080 is up to you, but this is how you should probably do it. You could do 32,000 minus 1,920 if you wanted to. So both of these are larger than 10. So therefore, we can use the normal approximation. We can use the normal approximation to the binomial, just to clarify, to the binomial. All right. So guess what we're going to do in part F? We're going to use the normal approximation. So where are we here? We want to know how likely is, so that translates to what's the probability, right? So we want to find the probability that we have at least 1,850 units of O-negative blood. We've checked that we can use the normal distribution, right? So we know the shape, we found the mean already, we know the standard deviation, so we have everything that we need. So let's just plop it down. We want the probability of at least 1,850 successes. Kind of using shorthand here. Just to summarize what we want to do. So we established that we're allowed to use the normal distribution. Great. So we've got our normal curve centered at the mean of, that we found was 1920, right? Yeah. And our standard deviation was, let's go back up there, 42.48293775. I would probably tell you how many decimal places to round to. Let's just use one decimal place, right? 42.5. Often I'll get you to use 2 decimal places or something like that. Depends on the scale that we're talking about. On this scale, out of 32,000, even one decimal or no decimal places might be fine, right? Kind of rough approximations. All right. So now we're back to a Z-score situation, right? And so 1850 would be to the left of 1,920. And so if I draw this kind of here, maybe, the probability that we're looking for right, is the probability that we have more than 1850, right? At least 1850. So the probability that we need is this area here. To find areas under the curve, right? Remember that we convert 1850 to a z-score, and then we can use the z-table to find the area to the left, right? The probability of having less than 1,850 O-negative donors, and then subtract that from 1 to find the area that we actually want. So we find that z equals x minus mu over sigma. So z is 1,850. X is always going to be the value that you're interested in, finding the area around, right? And so minus mu, that's always going to be at the center, 1920, divided by 42.5. 1850 minus 1920 divided by 42.5, I get a z-score of negative 1.647058824. We have to round z-scores to 2 decimal places, right, in order to use the z-table. So z is approximately negative 1.65. Okay. So now we can go to our z-table. And negative 1.6 is here. And if you don't have a copy of the z-table, I've got extras up here. Negative 1.6, what was the second decimal? 5, thank you. So now I'm gonna go across here. 0.0495 is the area to the left. So we can say the probability that z is less than or equal to negative 1.65 is equal to 0.0495. You can say that. Or you can say it in words, right? It's going to be a lot longer. That's why we have this probability notation, but it's kind of nasty if you don't like working with it. So you could say, or using the z-table, we find the area to the left of z equal to negative 1.65 is 0.0495. These two things are saying the exact same thing, right? In fact, usually people don't want probability notation. So I tend to just always use that same blurb, right? But until you start kind of reading it for what it is, right? When it's new and it's kind of like, I don't know what's going on, I just say this blurb and then I move on. But you're just telling me what you're doing, right? You use the z-table and you found the area to the left of the z that you calculated is the table entry, right? 0.0495. Right. Therefore, the area to the right of z equal to negative 1.65 is 1 minus 0.0495. 1 minus 0.0495 is 0.9505. we always want to talk about this in terms of the question that we're trying to answer, right? And so the question was, how likely is Canadian Blood Services to meet its need of at least 1,850 units of O-negative blood? The probability that they'll meet their need of 1,850 units of blood is 0.9505 or 95.05%, right? Depending on how you like to word it. So the probability the Canadian Blood Services, let's just do CBS, even though that's Canadian Broadcasting. They're very concerned. But let's just save on some writing. So the probability that the Canadian Blood Services meets their need of 1,850 units of O-negative blood is approximately 0.9505, right? Or 95.05%. There. Pretty nice. Okay. So we say approximately, right? Because first of all, we use the normal approximation to the binomial, so it's not exact, right? And we also approximated our standard deviation, so that's not exact anymore either. So we're doubling up on approximations. So at best, right, we can say that this is an approximation, but it's, you know, going to be around 95%. That said, you want to keep all 4 decimal places for your probability, right? Because that's from your table. You don't want to truncate that. You want to keep all those 4 decimal places. All right. Nice work, guys. Yeah, okay. Cool. Let's talk about the Poisson. Ho, ho, ho. And it is just the name of the guy, of course. Simon Poisson. He's French. Shoot, I should have said he's Turkish or something. I'll be like, that's weird. And wouldn't that be funny? 6.4. The Poisson distribution. Oops. So I've already warned you once, but I'll warn you again. We're not going to spend much time on the Poisson. It doesn't come up on the final. You'll see how to calculate Poisson probabilities in the lab. So I'm just going to run you through the situation. How do we calculate these things? But we're going to do actual calculate. We've got a couple of examples, and then we're just going to parking lot it. Right, so, one thing that I wanted to point out from assignment 6, there's this is completely kind of unrelated. Assignment number 6, I think it starts off and it asks you, what's the probability that Z is less than this, greater than this? And so you use your Z table to find it. But one of the question asks something like, what's the probability that the absolute value of Z is, let's say, larger than 2? Okay. We have to think about how the absolute value behaves, right? The absolute value, if you have a negative value and you take the absolute value of it, it drops the negative, right? And so what happens if you're looking at the absolute value is at Z equal to -2, the absolute value of z, if z is -2, would be 2. Right? And up here, if z is +2 and you take the absolute value of 2, you get 2. Right? So either way, you get a value of 2 for z. You want to know what's the probability of being greater than either of these, right? And so greater in the negative direction, right, would be to the left, because the absolute value of -3 is 3, which is greater than 2, right? -4 is 4, greater than 2. And so the area that you're going to be looking for is this area. And so plus this area. I know I said and, but I guess we could say or. Keep with our or is adding and is multiplying, right? But you want to look at those two areas combined, right? And that's your probability. Yeah.
So quick question on that. If you found the area of one of those, could you just multiply it by 2?
Sure can. Yeah. So because of symmetry, right? And so the more that you use your Z table and your Z distribution, you'll start to find shortcuts, right? You could say, okay, well, I can find the area to the left of -2. Because of symmetry, if I flop it to the other side, that area should be the same size. So then I can just multiply it by 2, right? And so as you get more used to it, right, you'll start to see those things. Because up until that point, you'll just remember me saying symmetry a lot. Oh, because of symmetry. Yeah, whatever. Okay. So Poisson distribution is a counting distribution. So as opposed to the binomial, we actually need to know the rate at which things are going to be occurring. Right? And so if we have, or if we know the mean rate, or just the rate, sometimes it's called. Sometimes we just call it the mean, sometimes we call it the rate, sometimes we call it the mean rate. All those kind of apply. So if we know the mean rate that events occur with, oh, that one's stuck. And one assumption that we are making is that each of these events are happening independently of each other, right? And so if we're counting things, right, we're counting customers through the door, for example. In the example that we're about to do, we're counting how many, I think, defects in some square yard of carpet or something weird like that, right? So we're counting things. And so we have to assume that these things occur independently, right? And that's not always the case. Sometimes we can kind of fudge it, just like we do with the normal distribution. We say, oh, it's approximately normal. Oh, I can boil it down to a success-failure situation. And so we have to say that, so that if we know the mean rate or the rate that events occur with, and the events occur independently of each other, we can use the Poisson distribution to find the probability of observing k events. So we can use the Poisson distribution to calculate the probability of k events. or I should say of observing K events. So it assumes that we know the rate at which these events are occurring with. And so it's not really that far-fetched, but the formula is a little bit weird. And so we can use the probability that X equals K, I think is what's on your formula sheet. Let me just make sure. The Poisson, yeah. Just like before in the binomial distribution, right? The probability that we have K successes, now that we have K observed events. So the probability of observing K events and I'm just gonna hit you with the formula and we'll break it down again, is gonna be lambda. That wasn't a very nice lambda, was it? There. Lambda looks like, sometimes I feel like I'm just teaching Greek letters all the time. So lambda looks like this. It's kind of have a like nice little tail on the top and okay. Yeah. Yeah, here they are on their phone. It's a Webster. No, it's a lambda. So you want lambda, which, spoiler alert, is just the mean or the rate, right? So we just use lambda for the mean or the rate, whichever you want to call it, or the mean rate if you prefer. So we've got lambda to the power of K. Right. We're trying to observe K events. And then we've got E, the constant, to the negative lambda over K factorial, really K. And we talked about K factorial or N factorial last day. N factorial or K factorial is K times K minus 1 times K minus 2 times K minus 3 all the way up to 0. Actually, not 0, all the way up to 1. Right, so 4 factorial is 4 times 3 times 2 times 1. Right, and so, but you should have, you probably have a button on your calculator that does it. Can I find mine? No, but that's okay.
Oh, I think for yours it's over the X.
Oh, really? X minus 1, you say?
X to the minus 1.
Oh, found it. Thanks. So on mine, it's over the X to the minus 1.
This is for factorial? Or?
Yeah, so you should have a little, on my calculator, it looks like a little X factorial button on my calculator, but it's in the second function, so you'll have to search up above, right? We'll see if we need it. If we're talking about, 5 factorial, we can easily just calculate 5 times 4 times 3 times 2 times 1, right? So, actually, let's circle this lambda here, although it occurs twice, but where lambda, which you just say lambda, is the rate or the mean rate sometimes a question might say, you know, you can assume it follows a Poisson with a mean of this, right? Then that's your lambda. Or things occur with a rate of this, that's still your lambda. It just depends on how information is given to you. Okay. And here, e to the negative lambda, right? You should have an e to the x button on your calculator, which we'll see in the example, right, when we do it. And k, right, has to be a count, so they have to be whole numbers. So k can be 0, 1, 2, 3, 4, 5, right? So it's a discrete distribution. And k may take on 3, on and on and on. So this is more going to be an exercise in using our calculator, right, than anything else, because all we need is the rate at something occurs with, and how many successes or how many events do we want to see, right? Now we're talking Poisson, so it's going to be events. Okay. So let's have a look at this example here. So a carpet manufacturer knows that the number of flaws per square yard in a type of carpet material varies with an average of 1.6 flaws per square yard, right? So here we're given the rate of flaws. What's the probability of no more than 2 defects in a randomly chosen square yard of material? So I've actually kind of put that in part C because first I wanted to go through and talk about, you know, can we use a Poisson, why, and what's the rate lambda, and then we can answer the question, right? Otherwise that would just be the entire question. So part A, can we model this with a Poisson distribution? Yes, we can. We have a rate, right? And we're counting the number of flaws, right? So since we are counting the number of flaws, and what's the other assumption, right? The assumption is that these defects or flaws are independent of each other, right? And I'll even not put it in bracket. Since we're counting the number of flaws, and we can assume, or we will assume, it's actually not that weird to think of defects happening in a cluster, right? But what we're assuming is that they don't, right? There's just singular defects across this piece of carpet. And we, you know what, I'll say we will assume, right? Sometimes we have to go that route where we're saying, hey, this is an assumption that I'm making. So, and we will assume defects occur independently at a rate of 1.6 flaws per square yard. Right. Because what we said for a Poisson, we need to be counting stuff. What we're counting has to be independent of everything else, right? And we need to know the rate that these counts are going to happen at. So since we're counting the number of flaws and we will assume defects occur independently at a rate of 1.6 flaws per second, we can use the Poisson distribution. We already said, right, in our blurb here, but part B asks what's the rate lambda. And so lambda, we're just going to use 1.6 flaws per square yard, but we'll just use it as a number. Part C, what's the probability of no more than 2 defects in a randomly chosen square yard of material? Use probability notation. Oh, come on. Formulas in probability notation, so it's not that bad, right? Because what we want is, in words, we want the probability of no more than 2 defects. One thing that you don't have to pay attention to in, in the class setting, because I would never really make you think about this, right? But in the real world, if you're trying to count stuff and you know the rate per square yard, you can only talk about the number of defects per square yard, right? And so then the units become important. For us, no, we can just, of course, it'll always kind of work out, right? So no more than 2 defects will, we can say that that's the same as the probability that X is less than or equal to 2, right? No more than 2, so we could have 0 defects, we could have 1 defect, or we can have 2 defects, right? And that satisfies all the different options that we're allowing, which is going to be the probability that X equals 0 defects. Probably the biggest thing that people forget about is the 0 option, right? Whether it be in the binomial, right, 0 successes, or in the Poisson, 0 counts. So the probability that X equals 0 plus the probability that X equals 1 plus the probability that X equals 2. Just like with the binomial, we have to do these individually, right? And so I like to break them up and look at each of the calculations together, and then I merge them back together later. If you are skilled enough to write them all on the same line, or however you want to do it, that's fine, right? I like to break them up. So I'm going to first find the probability that X equals 0. So now, actually, let's rewrite the formula just before we get started here. So we've got the probability that X equals K is what? Lambda to the power of K times e to the negative lambda over K factorial. Lambda to the power of K, e to the negative lambda over K factorial. If we want the probability that X equals 0 to start, lambda is 1.6, K in this case is 0, and that's all we need, right? Looks like we need more, but it's actually not, right? That's all that we need. And so we've got 1.6 to the power of 0. Anything to the power of 0 is just 1. And then e to the negative lambda, so that's e to the negative 1.6 over 0 factorial, which is on your formula sheet. I really hope it is just 1, right? So 0 factorial is just 1. So something to the power of 0 is 1, and 0 factorial is 1. So we get 1 times e to the negative 1.6 over 1. I'll make a little note here. 0 factorial is just 1. And also here, what we said was x to the power of 0 is just 1 for any x. So all we need to do here, it looks like, is just e to the negative 1.6. So you should have an e to the power of something button on your calculator. I found it. Depending on the calculator that you're working on, and this is, it depends. Like I've had calculators where I have to put whatever I want the power to be first, and then I hit the e to the x button, right? Or I hit e to the x and then feed it whatever I want in the power. So you're gonna need to make sure that you get the same value that I do, just to get to know your calculator a little bit. So e to the negative 1.6, I get 0.201896518. So make sure when you're working on your calculator that you get the same result there. All right. That's 1 down, 2 to go. The probability that x equals 1 is going to be, again, lambda is 1.6 to the power of k, which is 1 in this case, times e to the negative lambda 1.6 over 1 factorial. Really 1. 1 factorial is just 1 again. But now we've got 1.6 times e to the negative 1.6. So let's do that. So times 1.6. If you still had it on your calculator like I did, then I get 0.32303442888. Only time that we really get to calculate anything is for the probability that x equals 2. We've got our rate of 1.6 to the power of 2 now, times e to the negative 1.6 over 2 factorial, which is still kind of boring. 2 times 1 is 2. So it's just 2. We have 1.6 to the power of 2. I'll just simplify here, 2.56, so that you can see where everything came from, times, and then we had e to the negative 1.6. We already found was 0.201896518 divided by 2. So I get times 2.56 divided by 2. I get a probability of 0.258427543. Now we can find these probabilities added up to answer the question. One thing I want you to think about is we can still use the 1 minus trick, right? If I wanted to know, oh, what's the probability of more than 1 defect, right? Then you could just do 1 minus the probability of no defects. Right? So you can still use that trick, except k, right, goes to infinity, so it's a little bit hard, right? You could, in theory, count an infinite number of defects in a square yard. Right? if we think about the rate being 1.6, right? So on average, right, I'm expecting about 1.6 defects per square yard. If we want the probability of less than 2, I'm expecting my probability to be pretty large, right? Because on average, I'm seeing 1.6 defects per square yard. If I can push it to 2, right, and count how many have less than or equal to 2 defects, that should be a lot of these square yards of carpet, right? So already I'm expecting to see a pretty large probability. Let's see if that's true. So the probability that x is less than or equal to 2 is the probability that x equals 0. And I'm just rewriting what we did earlier, plus the probability that x equals 1, plus the probability that x equals 2. And if I knew how to store values on my calculator, it's still on my to learn list. I would have probably stored these, but instead I'm going to cheat and just copy paste so I don't screw them up. You've got them in front of you, but I have to scroll around like crazy. This one I've got 0.258427543. So if I add these probabilities, I've got the 0.258, so plus 0.32303444288 plus 0.201896518. I get a probability of 0.7833584898, which is pretty large, exactly like I was expecting it to be. So much for my dream of starting chapter 7, I think. Okay, so but what I need you to do for next week is I need you to read 7.1, 7.2, and 7.3. Those are the key ones. So read 7.1 to 7.3. Oops, I should say 7.3 for next week. It's going to be a lot, so it'd be really helpful if when I'm saying it, it's not the first time you're seeing it, but potentially the second or third time that you're seeing it. Hopefully we can get things together. All right. Sayonara. Bye, guys.